Welcome to our Module 4. We'll start with a discussion of transformations of functions and symmetry. These ideas are useful for the following problem. Suppose you're given a function that you wish to plot. What tools do you have at your disposal? Well, the naive approach, which works in some cases, is to pick many different input values and compute f at those values. So this gives you lots of pairs, f of x paired with x. And I can plot those in the Cartesian plane or the xy plane. How many points you need to do this for depends on how quickly you can see the pattern. In general, you might find it very time-consuming, especially without a piece of technology, to be able to do this efficiently. A better way is to say, remember certain basic atoms of functions, things like simple polynomials, exponential functions, basic trig functions, and then learn how to build more complicated functions out of those via things like reflections, things like translations, and understanding foundational properties of functions, ideas like even and odd symmetry. With these tools, your ability to plot functions expands dramatically, and you don't necessarily need to use technology for this. For the CLEP exam, a very large portion will be without a calculator. So if you're asked to understand the plot of some function that's not simple, these tools are invaluable as you approach that problem. So let's start with the notion of symmetry. The idea behind symmetric functions is that the plot of the function looks the same on two sides of some line. So in the case of what we call even symmetry, the picture is the same on both sides of the y-axis. If I reflect over the y-axis, the picture is the same. Here's another example. So the idea is that the two images are mirror images of themselves. I can imagine just drawing the picture on the right half of the y-axis and then reflecting it over the y-axis to get the entire picture. Now, of course, this is a very special property. Most functions don't have this type of nice symmetry. What are some examples of functions that do exhibit even symmetry? So many even degree polynomials have this type of symmetry. And that's not so hard to remember. Even symmetry, even degree polynomial. Not every even degree polynomial has this, but many do. Other things include cosine of theta. That as a function of theta is even. And we can see that by going back to the plot. Here is a rough picture of cosine, and you can see that I have symmetry about the y-axis. The second type of symmetry you ought to know for the CLEP exam is what's called odd symmetry. I think this one's a little bit trickier to understand. Instead of just reflecting over the y-axis, I'm going to do a double reflection. First, I reflect over the y-axis and then the x-axis. So let's look at some pictures here. On the left, I have the plot f of x equals minus x. So to illustrate the type of symmetry I'm interested in here, first I reflect over the y-axis. And then over the x-axis. On the right, I have a more complicated function, f of x equals x cubed plus x. To show the symmetry, I'm going to do the same thing. First, I'll reflect over the y-axis and then over the x-axis. So reflection 1 and 2. Another way to think of this type of symmetry is symmetry by reflecting over the line y equals x. So I have these two notions of geometric symmetry. Now, one might ask, well, what about reflection over just the x-axis? Well, I claim that if any function had that type of symmetry, well, it wouldn't be a function, because then I would have two values at every input. So we don't talk about this because it would ruin the definition of being a function. So how do I quantify symmetry mathematically? Well, we do it in a pretty nice way. We say that a function is even if f of x equals f of minus x. So if I put the input in, that's the same as if I put negative that input in. For odd symmetry, I have that f of minus x equals negative f of x. And this accounts for the fact that I do a double reflection. First over the x-axis, that refers to the minus sign on the outside, and then over the y-axis, which refers to the minus sign on the inside. So for these three functions, let's just practice and check whether they're even, odd, or neither. So to check, I'll plug in f of minus x and see if I get f of x or negative f of x or neither. If I can show that f of negative x is equal to f of x, then I've shown it's an even function. If I can show that f of negative x is negative f of x, then I've shown it's an odd function. And if I can show it's neither, then I've shown it's neither even nor odd. So in this case, I have negative x to the fourth, which is just equal to x to the fourth, which is f of x. So this implies it's even. And we can see that from our little sketch. F of x equals x to the fourth looks like a parabola, hence even. Let's look now at f of x equals e to the x. So I'll plug in minus x, and I get e to the minus x, which is not equal to e to the x, so it's not even, and it's also not equal to negative e to the x. So this implies it's not odd. So we conclude that e to the x is neither even nor odd, which makes sense given its plot. This does not have even symmetry, nor does it have odd symmetry. And for our last example, we'll look at cubed root of x. So plug in minus x. Can you even take the cubed root of a negative number? That's an important question. And the answer is yes, and it preserves the negative sign. So this is negative cubed root of x. So negative f of x, and this implies that I have an odd function. So what's the picture? Well, we've already seen it. It looks like this. So I have that type of special even or odd symmetry, where first I reflect over the y-axis and then over the x-axis. So keep in mind that when discussing odd symmetry, it's not necessary to do y then x or x then y. Either order is sufficient. Having discussed symmetry a bit, let's introduce techniques to build plots of functions from basic atoms. So the idea is that if I know how to plot f of x, these rules will tell me how to plot f of x plus something on the inside or the outside. These will correspond to translating the function either left or right or up or down. And I can also deal with reflections by replacing x with negative x or putting a negative sign on the outside. So these four techniques are very valuable to us. In the case that I have x on the inside, this corresponds to shifting by the left or the right. So this is a lateral transformation. Whether you go left or right depends on the sign of A, whether it's positive or negative. If I have a shift on the outside, then I shift up or down. And again, the direction I shift up or down depends on if the number is positive or negative. So what if I replace x with negative x? Well, that's going to flip me over the y-axis. So this is a reflection over the y-axis. And notice that the negative sign is on the inside. If the negative sign is on the outside, then I flip over the x-axis. So again, this is inside and outside. So this is a flip over the x-axis. So it turns out to matter a lot whether the shift is on the inside or on the outside. And this impacts the domain if it's on the inside and the range if it's on the outside. So let's look at some examples. So suppose I have f of x equals negative quantity x plus 2 squared. So let's use f of x equals x squared as an atom. So this is one of those pictures that hopefully you have in your mind. And what we'll do here is apply the transformations to see what the new plot is instead of plotting every value. So first, we shift by 2. Now, which direction do we move in? Well, let's check our rules. I'm shifting by a positive number, so I move to the left. So I'll shift over 2. And this gives me f of x equals negative x plus 2 squared, no negative sign. And now I'll apply the negative sign. So it's on the outside, which means I flip over the x-axis. And here is what I'm looking for. F of x equals negative x plus 2 squared. So compared to, say, picking many different values of x, plotting the y values, and then trying to connect the picture together, we can just plot a function that we know, f of x equals x squared, and then apply these transformations successively to see the bigger picture. So let's look at another example. Here we have f of x equals 1 minus, natural log of 1 minus x. So in this case, as an atom, we'll use just plain old natural log, which we know some of its values. So it looks something like this. Now, first I'll apply a reflection on the inside to account for the minus sign. So here's a reflection to account for the negative sign on the inside. But I'm not done yet. I also have a plus 1 on the inside. So that's going to translate me. Which way does it translate me? Let's check the rules. It's a positive number, so it'll translate me to the left. Or rather, to the right, in this case. Let's use a different color. So it looks something like this. Now, so let's label it. So we can check if this makes sense by plugging in 1 or 2 simple values. So plug in x equals 1, and I get natural log of 0, which is not defined. That's where I have this asymptote. So good, I have an asymptote at x equals 1. And then plug in x equals 0, and what do you get? Well, you get natural log of 1, which is 0. So good, I did this picture correctly. So in this case, we have a translation and a reflection. And you should be comfortable with understanding these types of things, even without the use of a graphing calculator. So one comment about using technology for the CLEP exam. Many times you'll be asked to say, make a qualitative statement about plotting. They might ask you, how many solutions does something like f of x equal g of x have? And they might be equations where it's very difficult to get exact answers. The only point I want to make here is that you can use technology or your own abilities to graph to estimate the solutions or how many there are, just by looking for the number of intersections. So suppose here is f, and here is g. Then the intersections are simply the solutions to this equation. So just from looking at the plots, I could say determine that there are 4 solutions. And if I had some technology, I could estimate what those intersections are. So just keep in mind that you may be asked to use plotting for questions such as finding solutions to equations or estimating the number of solutions that there are. And if you just look for the intersections of the two curves, you should have no problem doing this.